Broderick. The title is Fast Robustness and Uncertainty with Hierarchical Bayesian and Coresets. Please.
Yeah, so far we've actually heard a lot about scalable Bayesian inference, so I thought that I would talk a little bit more about our work on fast quantification of robustness, and then along the way I'll talk about scalable Bayesian inference, and at the very end talk about this Coresets work. Okay, so there's a lot to like about Bayesian inference, of course. We can have these complex modular models that let us share power across different experiments. Or we can have these models of complex physical processes, and what's particularly nice is at the end of the day, we get a full distribution over our parameters, our unknowns. So if I'm interested in a point estimate, I can query that distribution for a mean or a median. If I'm interested in an uncertainty, I can query that distribution for a covariance or quantiles. And of course, the way Bayesian inference works is I start off with a prior, I choose some prior, and that represents my knowledge or lack thereof about the parameters theta. I choose a likelihood, the probability of my data x given my parameters theta. And so, this just sort of encodes the relationship between those two, and then finally I use Bayes' theorem to calculate the posterior, the probability of the parameters. Now that I've seen the data, what do I know after having seen the data? So in theory, that's it. We're done. That's Bayesian inference. We have this likelihood and this prior, we calculate the posterior, and we can query it for anything. Move on. Of course, in practice, the reason that we have so many talks about this and there's so much ongoing work in this area is that there are actually a lot of practical difficulties to making this work. So for instance, the very first thing that I needed to do is I needed to choose a prior and I needed to choose a likelihood. And those can be potentially tough choices. I'm going to focus here on the prior a little bit, but the likelihood is also a potentially tough choice. But if we think about the prior for a moment, well, I have to encode my knowledge about these parameters going into the problem in a distribution. That might be something that's just hard to do. Or it might be that we're all very busy people, and so I actually only have so much time to work on this, and I could encode my prior totally as a distribution if you gave me enough time, but I don't have enough time. And so in the time you give me, maybe there's actually a range of priors that would fit what I've said so far. This is also a potentially subjective thing. I'm going to be talking about an application in microcredit, these small loans to individuals in impoverished areas, and the hope is that they'll help raise people out of poverty. Well, I might have some ideas about microcredit, and you might have some ideas about microcredit, and they might be slightly different. Or I might have some ideas about microcredit, and if you ask me next week, I might have a slightly different prior that I write down. And I want to know that under all of these circumstances, all of these reasonable priors that you and I might come up with together, that what's going to happen when we apply Bayesian inference? Is it going to be the case that we apply Bayes' theorem and we get exactly the same posterior for all intents and purposes, and we get the same decisions? Or much more problematically, is it going to be the case that actually we get different posteriors and different decisions? And so in the first case, I might be pretty happy with this analysis. I'm ready to move on to the next thing. In the second case, though, I might need to sort of dial it back a little bit, think, hey, should I be collecting more data? Should I be thinking more about my model? And should I be revising that? And there is an element of scalability here, so in a couple of different ways. So one is, this is increasingly a problem with the sort of complex models that large data sets enable us to fit. And so as we get these more and more complex models, we're more and more, we have the potential to be reasoning about parameters that don't necessarily correspond directly to our physical intuition, and so we have to think about, what if we had changed our beliefs about those in some ways? And also, we want to do this kind of robustness quantification. We want to know how much perturbing our assumptions changes our decisions, changes our posteriors. And we want to do that in a fast, easy-to-use way. We don't want to have to do some sort of ad hoc analysis where we run a posterior for one model, we find a posterior for another model, and then we hope that that was enough. Okay, so let's say now we've somehow have something like this. We're able to specify our prior and our likelihood, and we're quite happy with those choices. Well, there's still a challenge, which is that we actually have to get the posterior. And of course, in any sort of modern problem, we can't just have a nice closed form for the posterior. We have to approximate it somehow, and this is what we've been hearing a lot about. This approximation can be pretty computationally expensive. And so one of the things that people have been doing recently is they've been saying, my Markov chain Monte Carlo is running forever. I need something that's much faster. And so they've been turning to variational Bayes, which has been quite popular for this sort of scalable Bayesian inference. But problematically, variational Bayes, can, for instance, this is one of the particularly problematic things, underestimate the uncertainty, in fact, arbitrarily badly. And so if one of the reasons that you're being Bayesian is that you really care about the uncertainty, this is something that you really want to report at the end, you really care about this value, then this seems really problematic. It seems like you can't use variational Bayes. And so I'm going to be introducing sort of two concepts here. One is linear response variational Bayes. And so the idea of linear response variational Bayes is that we're going to use a perturbation argument to correct variational Bayes for the uncertainties and also get robustness quantification. Now, a problem with variational Bayes, and also check out this Opper and Winther 2003 paper, which uses some similar ideas back in the day for uncertainty quantification. But an issue with variational Bayes in general is that it has this nice empirical form. So we find that it works well on some large-scale problems. And in fact, that's sort of the general direction that a lot of this large-scale Bayesian analysis is taking recently, that, can we make some approximation, and maybe we can even throw out some theoretical guarantees like detailed balance and MCMC, or add in some extra approximation to get things to run really fast. But what we'd really like is to have fast methods that also have guarantees on quality. And so that's where I'll talk about coresets for Bayesian inference. Okay, so in the remainder of the talk, I'm going to start by sort of, recapping how variational Bayes is an alternative to Markov chain Monte Carlo, and in particular this challenge that it faces, this uncertainty underestimation. And I'll talk about how we can use this perturbation idea to get accurate uncertainties from variational Bayes. But one way that you could think about the whole first part of this talk is that I'm just building up to robustness quantification. So really this robustness idea is going to be, we make these assumptions about our model, and if we perturb those assumptions a little bit, what's going to change? How is our model going to change? How are decisions going to change? And so all of the rest of this is sort of building up this perturbation idea. And then, the reason that we're working in variational Bayes, at least for the moment, is that these derivatives or perturbations are somehow easier in this optimization framework that variational Bayes defines. But we don't have to work in variational Bayes. And so at the end, I'll say a bit about using coresets as a way to, again, get these sort of theoretical guarantees on the quality of Bayesian inference. Okay, so let's start with variational Bayes. So variational Bayes makes an approximation to the posterior. So in general, our posterior could be some crazy high-dimensional thing. Obviously, I can't plot that, so I just have this little cartoon here. And we want to find some approximation to it. So our exact posterior is this p of theta given x, and our approximation is q star of theta. And everything I've said so far is not specific to variational Bayes. I mean, this is true of Markov chain Monte Carlo, anything that's finding an approximation to our posterior p of theta given x. What's specific about variational Bayes is how we find that approximation. So we imagine that out in the world somewhere, there is a set of nice distributions. And I've depicted them here with this green blob. So what are nice distributions? Distributions that we can do the things that we want to with. I said in the beginning, we want to query to get point estimates, to get uncertainty estimates. So we want to find distributions where we can calculate means. We can calculate variances. We can calculate normalizing constants easily. These would be nice distributions. And the sort of sad fact of life, and the reason that we're even talking about this, is that our exact posterior is just not a nice distribution. We wish it were, but it's not. And so we have to approximate it somehow. And so variational Bayes is going to say, well, let's form our approximation by finding the closest of the nice distributions. Where for variational Bayes, close has a very specific form. We're minimizing the callback-Liebler divergence in a particular direction. So remember that callback-Liebler divergence is not symmetric. So this is a particular direction. Okay, so why callback-Liebler divergence? Why this particular direction? There are plenty of actual distances between probability distributions that we could be using. Why are we doing this one? And I think the real reason here is that it seems to be very practical. We can come up with nice, simple, easy-to-use algorithms for this case. We can get reasonable point estimates and predictions in a variety of applications. And of course, it's very fast. So again, the reason that we're not just running traditional Markov chain Monte Carlo on everything that we have is that we are having these problems with scalability. Certainly a number of talks have brought that up. And in particular, we've shown that we can make this streaming. So we aren't necessarily able to hold all of our data in memory. What do we do then? We want to have a streaming algorithm. We can distribute across a parallel architecture. And so, for instance, if we run on 3.6 million Wikipedia articles or 350,000 articles from Nature, we can run in just a matter of about an hour or a couple of hours. Okay, so that's great. I mean, it sounds like we have something that's pretty fast. It's scalable. Perhaps it could be even more scalable if we distribute it across more cores. And we get a full distribution, Q star of theta. I mean, if we want a point estimate, we can query that for a point estimate. If we want a covariance, we can ask that for a covariance. If we want a 16th moment, we can get it. It's a full distribution, Q star of theta. And here's the key point. Just because this is the closest of the nice distributions doesn't mean that it's actually close in any sort of meaningful way, that the posterior mean is close, that the posterior covariance is close, et cetera. And the way that this is usually particularly problematic, because we think that at least we see reasonable point estimates in a lot of applications, the way that this is usually particularly problematic is the underestimation of uncertainty. Okay, so to see what goes wrong with uncertainty, let's look a little bit closer at what's going on here. And let's look at a toy example. So here, imagine that I have a super simple posterior. I would never have something this simple in practice. But it's a really simple bivariate normal over theta 1 and theta 2. So imagine this is my exact posterior. And it's so complicated that I have to approximate it with variational Bayes. Again, toy example. Okay, so I'm going to try to minimize the Kale divergence between Q and this exact posterior. So the sort of key thing that I want you to notice at this point is imagine that I'm looking in this area of the theta space where there's very little mass. If there's very little mass in some area, P of theta given x is small. And so if Q of theta is large in that area, then we'll have quite a large contribution to the Kale divergence, and we won't choose that Q. And so in general, at a cartoonish level, we're kind of fitting our approximating distribution inside our exact posterior. Okay, so to see what actually happens, we still have to fully define our actual optimization problem. So we said what it means to be close, this minimizing the Kale divergence. What does it mean to be nice? Well, again, we think about nice distributions where I can calculate means and variances and normalizing constants. Well, what's a nice distribution? A low-dimensional distribution is a nice distribution. That's where I know how to do these kinds of things. And so the idea of mean field variational Bayes, a particularly popular variant of variational Bayes, is that we take our approximating distribution and suppose that it factorizes. So really, I'm using sort of shorthand here. Each of these Q's could be different in every dimension. But I'm essentially just saying that there's going to be an axis-aligned approximation to this exact posterior. Okay, so if I'm going to fit an axis-aligned approximation to this exact posterior, and it's going to be inside my approximating distribution, what's that going to look like? This is the approximation that we get. This is the mean field variational Bayes approximation. And so you can immediately see it's a bad approximation. In particular, even though the point estimates are right, I'm underestimating the variance. In fact, I can make this as arbitrarily bad as I want by making the green distribution thinner, and I'm getting no covariance estimates whatsoever. I mean, by definition, by construction. And so if these things matter to me, this is going to be a big problem. I really care about getting the correct uncertainties. Okay, so how can we correct this? Okay, well, let me just mention first, in some sense, this is a very old problem. People have been aware of this for sort of, a very long time, at least, back to Mackay's textbook in 2003, and I'm sure before that. But it's also a very modern problem in the sense that a number of people are saying, I'm stuck between a rock and a hard place. I really want to have this fast variational Bayes inference, but I have to, go and do something else because this is just going to give me a really bad uncertainty estimate, and I really care about uncertainty estimates. And so increasingly we're seeing a lot of things where people get rid of detailed balance or add an error via like sort of distributed communication. And so we're sort of throwing out some of the theoretical guarantees of Markov chain Monte Carlo. And so what if instead we take variational Bayes and make it more accurate? Okay, so this is the idea of linear response. And so at a high level, how does this sort of perturbation framework work? Well, let's think about, if I had access to a cumulant generating function, I'd be all set. So remember that the cumulant generating function is the log of the moment generating function. So here we have our parameter theta. The expectation is over whatever distribution we're interested in. And t is sort of the input to the cumulant generating function. And so the cumulant generating function generates the cumulants. So the first cumulant is the first derivative of the cumulant generating function set t to 0, and we get the first cumulant, the mean. The second cumulant is the covariance. So if we're interested in the exact posterior covariance, we look at the cumulant generating function for the exact posterior, and we get out sigma, which is what we'll call the exact posterior. Now, on the other hand, we could have taken the cumulant generating function for this sort of bad, approximating distribution, Q star, And in fact, that would just be some matrix V, it would be block diagonal, and it would underestimate the variances in general. Now, where does linear response come into all of this? Well, what we're going to do is we're going to take the log of the exact posterior and apply a linear perturbation. We have this linear perturbation, and that defines, you know, when we make this perturbation, that defines a new distribution. We could call it P sub t, so long as we normalize that distribution. And so when we normalize P sub t, you can easily check that, in fact, the normalizing constant, or the log of the normalizing constant, is the cumulant generating function. So somehow this linear perturbation contains the information of the cumulant generating function, which in turn contains the information of the covariance. So maybe this isn't such a crazy thing to do. Okay, so now I'm going to ask you to do something totally, you know, that you would never do in practice. This is beyond the pale. But we'll find that, in fact, it's a useful thought experiment. So what I'm going to do is I'm going to say, okay, so for every one of these P sub t's, imagine that you fit an approximation Q sub t star with mean field variational Bayes. Now, we don't want to fit more than one mean field variational Bayes approximation, because again, we're interested in fast algorithms. So we definitely don't want to fit an uncountable infinity of these. That would be too many. But let's just imagine that we're doing it for the moment. Okay, so we fit these approximations. And what we really want to approximate is this uncertainty, this covariance matrix. Now, we can't just put Q star in here, because we know we're going to get the bad V matrix, the block diagonal V matrix out if we do that. And we can't just calculate the whole thing, because we can't calculate sigma in general, because we don't have access to the exact posterior. And so what if we do something sort of in between and we approximate just this part of the derivative? Well, remember, this derivative is just the expectation under P sub t of theta. And we think that variational Bayes gives reasonable point estimates in a variety of applications. And so if we're willing to believe that, then maybe we're okay with the approximation that says we're going to take this expectation and approximate it by the expectation under Q sub t star. So this is the one approximation that we're going to make. Everything else is just true. And this will be exact whenever these two are equal. Okay, so if we make this approximation, we can call the result sigma hat, our linear response approximation to the covariance. Okay, two things. One, I'm going to ask you to remember this form, this d dt of expectation P sub t of theta. We're going to see it again later. Two, this isn't a useful formula yet. So here we have this dependence on t. We don't want to calculate a lot of mean field variational Bayes approximations, so we have to do something about this. So let's do something about this first. Okay, so how do we get rid of t? Well, we're going to make one more assumption. We're going to say, hey, you know, mean field variational Bayes, we were looking at the nice distributions, the low dimensional distributions, or the distributions that factorize into low dimensional distributions. So those are nice, because they let us calculate means, they let us calculate normalizing constants, covariances, et cetera. But you know what would be really nice is if our distributions were exponential family. Then we can definitely calculate all of those things. And so this is actually a common assumption that's made in practice. We're going to assume that, in fact, our Q sub t approximating family is exponential family. If we do that, then it has some mean parameterization m sub t, and we can simplify sigma hat to be the inverse of the square, or sorry, of the second derivative of the Kale divergence. So here, m, again, is just the mean parameterization of q, and m star is the mean parameterization of q star. And in fact, this becomes an even nicer, simpler formula. So here, V is that bad block diagonal matrix for mean field variational Bayes. So we run mean field variational Bayes, we get out our point estimates, we get out this bad estimate of the uncertainty, and then we can think of this as being a correction, this I minus VH. So I is the identity matrix, H is a matrix that we can calculate from the form of the prior and the likelihood and automatic differentiation. So a really key ingredient that's making a lot of this run is automatic differentiation. Okay, so a few things before we see this in practice, before we see the results that we get on some real data. One, this matrix is clearly symmetric, which is what we would hope for a covariance matrix. It's also positive definite so long as we're at a local minimum of the Kale divergence, which we hope we would be by running any sort of reasonable optimization algorithm for mean field variational Bayes. And we made this one assumption. So when this assumption is correct, when these sort of means track each other, then the LRVB estimate is exact. So this would be true, for instance, if the exact posterior were a multivariate normal. More generally, where posteriors aren't defined by their first two moments, their first two cumulants, this will be an approximation. So we want to check it. Okay, so let's look at this example. I talked to, I said we have this microcredit data. So we've been collaborating with Rachel Meager, an economist at MIT, and she's studying microcredit. So she's really interested in understanding, do these small loans really help bring people out of poverty? Are they effective? And so there's data, these randomized controlled trials take place in 7 different countries at 7 sites, each of which is in a different country. There's between 900 and 17,000 businesses at each of these sites. And so the model that we're going to be using here is sort of a classic hierarchical model that respects that sort of, while there's some shared microcredit effect across countries, we imagine there's some idiosyncrasy about each of the individual countries. Okay, so we're going to say that the profit of the nth business at the Kate site is modeled as follows. So by the way, I'll just meta comment. There are a lot of ways to measure how microcredit is working. This is just one particular one that we'll look at right here. Okay, so we're going to have this normal distribution. The profit is normally distributed around some base profit for each of the different sites. That'll be the mu k. And then we have a term that represents sort of the microcredit effect. So first we have an indicator of whether or not microcredit was applied. So this is something we know from the randomized controlled trial. And then tau k is the sort of site-specific microcredit effect. How much is microcredit helping at this site? And then finally, we have some noise specific to each site. Okay, we don't know mu k, tau k, or sigma k squared. And so let's be Bayesian and put some priors on those things. We'll say that mu k and tau k are normally distributed around some sort of worldwide base profit and microcredit effect. And so really, in some sense, tau is the particularly interesting thing here. It's, if anything, the most interesting parameter. How much is microcredit helping in general, or hurting maybe? Maybe tau could be negative. We don't know. So we'll have a prior on the noises, the sigma squareds. We'll have a prior on mu and tau. The inverse Wishart would be the conjugate prior for C, but the separation in LKJ prior has some nice properties. And so we'll use that. Okay, so what we want to do is we want to check, let's find the posterior over all the parameters here, the mu k's and tau k's, the mu and tau, the sigma squared, the C, and see, are we getting good estimates of those quantities? Okay, well remember, there's this sort of, one assumption that we made, that the means are well tracked by mean field variational Bayes. So first of all, we want to get those means, and second of all, we want to check that that assumption is true. And so to check that assumption, we'll run Markov chain Monte Carlo for a really long time and just double check that we're getting the right value. Why not just run Markov chain Monte Carlo in general? Well, in this case, if we get 2,500 Markov chain Monte Carlo draws from Stan, that takes on the order of 45 minutes, whereas all of mean field variational Bayes, together with this linear response correction, together with a bunch of sensitivity measures that I'm building up to but haven't yet shown you, and not taking advantage of distributed computing or anything like that, takes just 58 seconds. So this sort of order of magnitude speed up can be really meaningful for a practitioner like our economist friend, because that means that she can iterate more on the economics, the interesting questions in her field, and not have to worry about what's going on under the hood. Okay, so here for each one of the parameters in the posterior, each one of the parameters in general, we're plotting a point which represents the mean as estimated by mean field variational Bayes, and the posterior mean is estimated by Markov chain Monte Carlo, and we see that they're sort of on the x equals y line that we're plotting, so there's agreement. And then since these means are so well estimated, we're not surprised when we see that, well, first of all, mean field variational Bayes underestimates the uncertainty sort of as expected, but then linear response corrects them to the x equals y line. And so this can be really important for this kind of application, because here we're really interested in saying, is microcredit effective, and should we make some decisions based on that? And so if we find that the microcredit posterior mean is $3 US purchasing power parity for every 2 weeks, and the standard deviation is 1.83 US purchasing power parity, we'll notice that the mean is 1.68 standard deviations from 0. And so as an economist, we might say something like, oh, it's not more than 2 standard deviations from 0, and so let's not make this policy because we don't have enough evidence to support that microcredit is helping people yet. But if we had used mean field variational Bayes, we would have underestimated this uncertainty. We would have been overconfident to the point that we would have said the mean was more than 2 standard deviations from 0. And erroneously, without support from the data, concluded that, yes, we should definitely go out and use microcredit and make some really important decisions based on this. And so here's a case where we really do care about getting these uncertainties correctly. Okay, I'll mention, we see this in a variety of other examples as well, so I'm just going to mention this microcredit one here. Something that you might be concerned about at this point is, oh gosh, you had this matrix inverse. That always seems scary. So, I minus VH, what is the size of that matrix? Well, it's number of parameters by number of parameters. Now, let's think about something like a clustering problem, a mixture model. There I'm going to have some parameters that are the means of the clusters, the shapes of the clusters. These are like global parameters. They don't change as I get more data points. But then I'm going to have these parameters that are like the assignment of each data point to a cluster. That's going to grow with the number of data points. It's going to grow linearly with the number of data points. And so I should be really concerned if I'm going to have something that's an operation between n squared and n cubed in the number of data points. That would not be scalable. That's sort of like the whole point. We want these scalable methods. Well, luckily, we don't have to worry. So we can decompose the parameter vector into a global component, alpha, and a local component, z. So again, these sort of parameters that grow with the size of the data. We can also decompose v and h, similarly, into the global component as well as a local component. And so now, if we look at the Schur complement, say of like sigma alpha hat, the alpha component of the covariance matrix, there are two inverses. There's one on the order of the number of global parameters, which maybe we're not at least quite as concerned about. And there's one on the order of local parameters. This is the really concerning inverse, the thing that we definitely don't want to have to invert a matrix that's number of local parameters, or number of data points by number of data points, basically. But remember, sort of the whole problem with V was that it was block diagonal. So it's going to be block diagonal in those local parameters. And H, actually, is going to be block diagonal in the local parameters as well. And the reason for this is that typically in a likelihood, when you look at the terms in the likelihood, the factor terms, those factors tend to include maybe global parameters together with local parameters, but they don't tend to include a bunch of local parameters together. And so whenever that's the case, which it typically is, we're going to get this kind of structure. So finally, I minus VH is going to be block diagonal in the local parameters, and in fact, we're going to get a linear operation in the number of data points, not something between squared and cubed. Okay, great. So we've talked about how we can get this kind of perturbation analysis, and so far we've really framed things in terms of these uncertainties for variational Bayes, but I promised you that we would talk about robustness. And if anything, robustness, I think, is much more natural to think about in terms of a perturbation analysis. We're starting from assumptions, and we're perturbing around those assumptions and saying, hey, if we changed our assumptions in any direction, how much would that change our final outputs? And so let's make that a little bit more precise. So we're going to start from Bayes' theorem, just as we did before, and now we're going to include some hyperparameter alpha in the prior, just to sort of emphasize that we're making a choice about the prior. So for instance, maybe our prior could be normal, and this would be just a typical hyperparameter like the mean and variance of that normal. But in general, it actually could be a sort of non-parametric perturbation. So maybe the alpha just says how much of like some other distribution we add to our prior. So it actually can be quite general. Okay, and then I'll introduce this notation, piece of alpha, to represent our posterior distribution, with sort of including this choice of alpha. And we want to define a notion of sensitivity. So again, thinking back to what we had at the beginning, we were saying, hey, I have some prior and likelihood choice that I make. I'm going to make these assumptions about my model. But if I change them a little bit, would I get the same results or very different results? How much would it change my results? Now, in general, the thing we're reporting at the end of the day, usually it actually isn't the entire posterior. It's typically some functional of the posterior. So for instance, something we were really interested in this previous example was the posterior mean. So we might be interested in saying something like, okay, if I change these hyperparameters, how much does the posterior mean change? So that would be the choice of, say, g is the identity function here. Okay, so one way that we can encode that is we can say, let's say that the sensitivity is the derivative with respect to alpha of this posterior functional that we're reporting, something like the posterior mean. Now, the key thing to remember here is, remember at the beginning, sort of nearish the beginning, when I said, hey, remember this form, this expectation p sub t of theta dt, or d expectation p sub t of theta dt. That's exactly what we're seeing here. We're seeing the same thing, only now I put alphas in instead of t's. So all that work that we did so far, we can just sort of immediately plug in here to get these sensitivities analysis. So here we say, oh, expectation, maybe we think in many cases that a point estimate is something that mean field variational Bayes or variational Bayes in general does okay. So we're willing to make this approximation, and so finally we'll say this approximation is our LRVB estimator of the sensitivity. And again, we say, okay, well, we want to simplify this, we want to get rid of alpha. So maybe we can assume q sub alpha is in the exponential family, and we'll get out a nice formula. So here, this formula now has three components. A comes from the form of G. If G is the identity, then A will be the identity. B comes from the form of the prior. If the prior is a conjugate exponential family prior, B will be the identity. And then the awesome part is that this whole middle thing is what we calculated already with LRVB for uncertainty estimates. And so if we did that correction, if we did that calculation, this is computation that was already done, and we can just plug it in here. So we just get this sensitivity out. Okay, so let's come back to our microcredit example from before. Even if you're some super microcredit expert like Rachel Meager, you might still say, there are so many hyperparameters, mu naught, tau naught, lambda inverse, eta c, d, a, and b. There's probably still some range that might be appropriate to put in here. And we want to know, if we vary over that range, is that going to vary our analysis? And so we can check how our sensitivity estimates are coming out of linear response variational Bayes. And again, we make this assumption that the means are well tracked, so this is just actually the plot from before. And now to check whether or not we're getting our sort of derivatives calculated correctly, let's just compare to MCMC at a couple of points. So the way that we're going to approximate the derivative from MCMC is we're going to run at 0.03, we're going to run at 0.04 for just these two values of a particular hyperparameter, and approximate the derivative between them and see if that estimates or it gives the same value as LRVB in that direction. But of course, we're getting other directions as well. And so again, we're looking at this x equals y line, and it does seem like we're getting reasonable estimates. Okay, so how would you use these sensitivities in practice? Well, again, let's think about this expected microcredit effect, tau. So we're going to look at the sensitivities on the scale of tau standard deviation. So we can look at them for these three hyperparameters and these two hyperparameters. You'll notice, by the way, off the bat, that these are very different scales. So at the top, we get changes on the order of sort of tens of tau standard deviations. Here we get changes on the order of hundredths of tau standard deviations. And now let's think back to our analysis. We said that the mean was 1.68 standard deviations from 0. And now we can imagine that maybe our economist friend comes along and they say, actually you could have changed lambda 1 by 0.04, and I don't think that should change your analysis. That would have been a totally reasonable starting point. Well, if I change lambda 1 by 0.04, the derivative up there is on the order of 9 tau standard deviations, so I want to add 9 times 0.04 to 1.68. I'm going to get a mean that's more than 2 standard deviations. So in this direction, that's not quite as interesting, but you can imagine things going the other way. Like we had done this analysis. We had found that the mean was more than 2 standard deviations from 0. We're going to go out and make microcredit a reality. We're going to make some big policy changes. And then we did this robustness analysis, and we found, actually, sometimes for very reasonable choices of the hyperparameters, the mean is not more than 2 standard deviations from 0. And so let's actually be a little bit more conservative. Let's go back to the drawing board, either collect more data or think about, are there things that we could add to the model, like covariates? Like, maybe does microcredit depend on certain aspects of the business or certain aspects of the individual that you're loaning to? Okay, so we've talked about how we can use variational Bayes and this perturbation idea with variational Bayes to get these uncertainties, and in particular, how that feeds into getting this robustness quantification. So hopefully this can be the sort of thing that, you want this to be the sort of thing that people do an analysis, and it's just an automatic part of the analysis, like probabilistic programming. Like they've got their model, they run it, they get this approximate posterior, and then they just automatically get a robustness quantification. So you don't have to sort of think of, here are some reasonable models that I could have chosen, but I also have to have inference for those and run inference and think about what I'm going to do, that this just comes out automatically. Okay, a couple of points. So one, I sort of phrased all of this as, let's work with mean field variational Bayes. So this is a particularly popular form of variational Bayes. Let's use that and then see if we can get these robustness estimates. And in fact, the results that I described here are a specific form of a much more general result. So it turns out we don't actually need mean field variational Bayes. You could do basically any form of variational Bayes, this optimization of finding the closest of the nice distributions. And this is really important. So there have been a lot of advances recently in variational Bayes, thinking about broader classes of models that we could use. And so this would incorporate that idea. Okay, but nonetheless, even when we think about these broader classes of models, there are still challenges. So like I said earlier, when we try to scale up variational Bayes, MCMC, try to make these streaming and distributed, typically what's happening is there's some loss in the guarantees that are associated. So with VB, we actually typically don't have a lot of finite data theoretical guarantees to begin with, but especially when we add in the streaming and distributed components, we lose those in both cases typically. And so what we'd like to do is we'd like to have the ability to do scalable inference, to do streaming inference, to do distributed inference at the scales that we're familiar with, that we can do these approximate algorithms with. But we'd like to do it with some sort of guarantee on quality. And so this is what we're going to be talking about with coresets. Okay, so the idea of coresets is fundamentally that we have this large data set out there. And I have this sort of cartoon of a large data set here. And this cartoon, or this large data set is quite large. And if we think about running Markov chain Monte Carlo on our data set, for instance, we have to iterate through that data set again and again. And as we do that, each iteration is an O of n time operation, and so this can be pretty expensive. And so what we'd like to do is we'd like to have a smaller weighted data set, for instance, that approximates our larger data set. And then we'll have sort of much less time that we have to spend on the iterations, maybe fewer iterations, and this will speed everything up. So this is the idea of a coreset, to get this smaller weighted data set that sort of represents the core of our main data set. So in this toy example, imagine that I have actually like a corpus of documents, and they're actually all about sports articles. And so maybe I have a bunch of articles about football because it's very popular, and I have fewer articles about curling because it's not quite as popular yet. And I want to summarize this data set somehow. And so I might imagine that I get one representative article about football, and because there are so many articles about football, it's going to have a very high weight. And I'll have one representative article about curling, and because there are fewer articles about curling, it'll have a low weight to represent that. Okay, and the reason that we're even looking at coresets is that where they originated in the theoretical computer science literature and the computational geometry literature, there are typically theoretical guarantees associated with them. When we run some sort of optimization problem on the smaller weighted data set, we find that we can get epsilon close to the full data set optimization problem. And in fact, we can sort of take more time to make that epsilon smaller. We also get these fast algorithms and error bounds on streaming and distributed inference, and so that's another reason that we're interested in pursuing this. Now, there have been some similar ideas in the past. So one of these is data squashing. Another is, if you look at the sort of recent and past couple of decades, big data Gaussian process literature. In both of these cases, we see that this idea of having like sort of a smaller weighted subset, or at least a subset of the data to run on, is there. But what's not there are the theoretical guarantees associated with that. So it's more of a heuristic kind of argument. Another thing you might think of is subsampling. Why not just uniformly sample the data? Well, a way to see what might go wrong there, sort of at a intuitional level, is to imagine in this picture that we subsampled our data, and maybe at the end of our subsample, because curling is such a rare sort of event, we could easily find ourselves in the position of not having any articles about curling. Now, it depends what we're trying to do, whether this matters or not. So if, in fact, we're employed by a curling sports manufacturer, like sports equipment manufacturer, then this would be horrendous. They really cared about those curling articles. That was really important to their bottom line, and so subsampling that away was a big problem. And so the way that coresets gets around this is it starts off by defining a notion of sensitivity. How much the output changes when we change the data points. And so for curling, this would be much more important if that were sort of our goal in the end. And so finally what we do is we do an importance sample according to the sensitivity rather than according to just the number of data points. And after this, we take the sensitivities and take the inverse to get the weights. And so we're left with this sort of coreset that we saw earlier. Okay, so what we're doing here is trying to develop this coreset idea, but now for Bayesian inference, with a focus on logistic regression. But we're hoping our ideas, and we're working on extensions of the ideas right now to more general Bayesian models, more complex Bayesian models. Okay, so, oops. Let me just. Just a problem with my animation here, so I'll just skip ahead. Okay, Okay, so what our Coreset project looks like for, oh, I don't know why this isn't showing. Here, let me just put it over here. Okay, so what Coresets look like for Bayesian logistic regression is we have to define a notion of sensitivity for each of the data points. So how much do they now affect the logistic regression decision boundary? So we first get those sensitivities. We calculate the sensitivities for each data point. And then, what we do is we sample the data points according to the sensitivity, like we saw earlier for the sort of more clustering-oriented example. So we sample the data points according to those sensitivities. And then finally, we get an inverse weight. So we get the weight by taking the inverse of the sensitivities for each of the data points. And this is finally our coreset. It's this weighted subset of our data that we can input into an approximate posterior algorithm. And so that's what we do. And so in particular, we can take our full data set, put it into Markov chain Monte Carlo, get our approximate posterior. And so for instance, if we do this for a web span data set on the order of 350,000 points and 127 features, so here the idea is we want interpretable prediction for whether web spam or whether something is spam, whether a particular website is sort of malicious, do anything like that. Oh. Oh, great, thanks. So we want to be able to interpret whether something is malicious and what features contribute to this. And so this would take on the order of 2 days for the full data set, using, in this case, MALA as our MCMC algorithm, whereas we take the coreset and put it into Markov chain Monte Carlo, and so both the cost of the coreset and Markov chain Monte Carlo takes on the order of just 1.85 hours. I'll just say that we can get these finite data theoretical guarantees. It's sort of the opposite, actually, of the nice sketching talk we saw yesterday. So our theoretical guarantees started by being about the evidence, and epsilon close bound to the log evidence. And actually, we were interested in trying to find out bounds to the log, to the posterior mean and the posterior variance. And so I'll talk about that in just a second. And we can get these this propagation of error, quantifying the propagation of error in streaming and distributed settings. And so let me just say something really briefly. Steve Scott, in his great talk about parallelizing Markov chain Monte Carlo inference, talked about 100,000 data points. That's nothing. We should be going way beyond that. And so one of the things that we looked at was this Criteo data set. So it's actually 4 billion data points for 7 days of traffic for people clicking on ads, and whether they clicked on ads and what contributed to that. So we're just going to look at 6 million data points right now, this subset of 6 million data points with 3 million features after one hot encoding. And if we run an alternative idea, so here what we're doing is we're approximating the likelihood as a function of the data, so not with the data itself, but just as a function, with a polynomial approximation. So this gives us a kind of a sufficient statistic. And once we have a sufficient statistic, actually we have this sort of trivially streaming, trivially parallel, sort of embarrassing streaming and parallel computations with minimal communication. And when we do that, we can run in 24 cores in less than 20 seconds. And so we think that we could actually get to quite a lot more data if we had more cores, and with sort of no additional cost. In fact, if anything, even less cost. And what's nice about this is we can get bounds on the Wasserstein distance, so actually bounds on posterior means and variances. Okay, so let me just sort of conclude here. So we have this linear response variational Bayes idea that we talked about in the beginning, which was this sort of perturbation idea. So we could use that to get these covariance corrections in variational Bayes, but also, I think, really excitingly, to get these robustness quantifications. So ultimately, we want to have the ability for robustness to be something that's just naturally a part of an inference algorithm, and not something that you have to sort of do all this extra work for. And then also we talked about this reliable inference using coresets, or more recently this polynomial approximate sufficient statistics idea. And so now we're working on extending these ideas beyond logistic regression, which some of our existing proofs sort of relied on certain aspects of that. And then also, I think it would be really exciting to get this together with the robustness stuff and be able to maybe prove, that we're doing so well with our robustness estimates. And so if you have any interest in prior perturbations, sensitivity to prior perturbations, and the second part isn't specific to Bayesian inference, sensitivity to likelihood or data perturbations, then we're certainly interested to hear about that. And I'll just mention a few of the papers that are relevant here. So the linear response variational Bayes for covariance paper appeared in 2015. The robustness paper, hopefully we're going to have on the archive soon, the journal version of that, but an earlier workshop version appeared in 2016. The Coresets work appeared in 2016, and again, the polynomial approximate sufficient statistics work, hopefully we'll have on the archive soon. Thank you.
You have a method for getting sigma in a mean field variational approximation. Is that the same sigma that you would get if your approximation was just a multivariate normal u sigma?
Yeah, so it's not quite the same as having done, well, okay, so ultimately what you want to do is you want to get the posterior mean and the posterior covariance. You want to estimate these things. And so one option is to have a full multivariate normal approximation from a full variational Bayes, like that's just the approximation. And another one is to have this, this mean field approach and then correct it. And so in the case where your true posterior is multivariate normal, both of these will be exact, like they will recover the actual posterior covariance, although I think our method will be quite a bit faster because you won't have this like iteration over getting the covariance parameter. And more generally, I think they're just going to be slightly different approximations.
Does this say anything at all about the situation where two people have radically different priors? You might have one belief, I have a radically different one. Does this say anything at all about that?
Right, right. So one thing that I'll say, so a couple of points on that. So one is this is a local estimate of robustness. And so it's about saying, you have this particular set of priors or set of likelihoods and you perturb that, what happens? And so if you have something that's truly different and can't be approximated by essentially a linear sort of Taylor series approximation, then this isn't going to get at that. Like you would need to actually sort of integrate along that path. But another thing to say is, to a certain extent, what we're getting at here is you have this choice of prior, and you might have been ambivalent about the things around it. And if you think that you were ambivalent around that, and you just wanted to know like what's sort of the worst case thing that would happen, then this is kind of getting at that idea. If you fundamentally disagree with somebody and you just have very strong subjective opinions in those two cases, then you're going to have your Bayesian output and they're going to have their Bayesian output. And actually, you should probably think more about like subjectively what you're saying. This doesn't say so much about the subjective aspect of like how you should choose a prior. What does that express? How do you come to agreements or disagreements with people? It's more just about for your if you feel like you are ambivalent around an area.